Okay, so we call this then a map projection because originally maps were made by projecting the shadows onto paper. So we've got three main categories: planar, conic, and cylindrical. And you're going to need to describe the features that you see on these slides. Again, you're writing what's in yellow on in the graphic organizer at the bottom of page 9. So in a cylindrical projection, imagine that you wrap the globe with a paper cylinder and you project the shapes onto the surface of the paper. Remember, we've got that light inside that's projecting it out, and then we trace the lines and shapes onto the paper. Then we unwrap our cylinder and flatten it out, and that's our map projection. Now, the projection is most accurate near the equator because that's where our cylinder was touching the globe, so that's where it's most accurate. But it's greatly distorted near the poles because, see, that's where we were absolutely not touching. That's the furthest points away. Mercator projection. Mercator projection is the most famous cylindrical map. You've probably seen one before, and once we look at all the projections, you're going to look at some videos that show you the difference between these different projections and the different problems of each. So Mercator's map was great for navigation. It was used for over 200 or over 400 years. So direction is really good. We know that Africa is south of Europe and southwest of Asia using this projection. It's not very good for size and distance. So if you're traveling, say, from Canada over to Greenland, you're going to see that there's some size mishaps there, and so distance is not going to be quite as accurate. You're going to be not getting to your end location at the time you would think, or after you've traveled the distance you think. So a conic projection, this time, instead of a cylinder, placing a cone over the globe. And again, we're going to, after we make our projection, after we project the shapes, we're going to cut the cone, flatten it out again. And like before, it's least distorted where the cone touches the sphere. It's really good for showing places like the United States because of where that cone would be hitting on the globe and the position of the United States. So most of the US would be in contact with the cone. Makes that nice little smile shaped map. Now, latitude lines, you'll notice over here on the conic projection, and over here on this one of the United States, you can see a little bit at the top, that they are curved. On a globe, these are actually straight lines. You wouldn't be walking, I mean, they circle the globe, but they don't curve at all. When you're walking, if you get on the equator, you will walk straight to go the whole way around the equator. A planar projection, or an azimuthal projection, sometimes also called a polar projection, where you put just a plain old flat piece of paper beside the globe, it's only going to make contact at one single point. And so as you move further away to the edges, it's going to get really distorted. Now, this is great for showing the poles. It's really accurate right at the center there. So in this case, you've got the North Pole right in the center. So the area near the pole is very accurate, which in our other projections would be least accurate. So if we want to show this area near the pole accurately, we're going to get the planar projection. Now, this is also good for seeing distance a little bit more accurately up at these northern parts of the globe. So if we're trying to go from like the United States over here to Japan, if we were looking on a globe, we'd say, oh, you got to fly across the Pacific Ocean. You probably trace that line of latitude right there. And that is not necessarily the direct route, okay, because you can go right pretty close to the North Pole. So map makers have a reason to choose what projection they are using. So you'll see at the top, you've got an important statement that says map objectives, and you need to highlight those things that the map maker is worried about. They're worried about area or the size, shape, distance, and direction. Based on which of those they need to be most accurate, that's how they choose the projection that they will use. we're going to skip through these. You do not have to write anything on the anything else in that graphic organizer that says area, shape, distance, and direction. Skip down to that next statement. Something that map makers do is exaggerate. So if we were, this is Pennsylvania, because up here is New York. So we know New York is north of Pennsylvania. So if we're looking here at this map, if we went and looked at a satellite image of the same place, we wouldn't see these roads as clearly. They wouldn't be this size. But if we're looking on a map of just a highway map, we need to make the roads more visible. So they are larger. If we actually went down here to the Grand Canyon of Pennsylvania and measured these roads going into it, using the scale of this map would not be accurate. We wouldn't get the same, the road would not be as wide in real life as it would appear to be on the map scale. So we have to exaggerate. It just makes them easier to see. They're not really that wide. The road signs are not going to be the same size, obviously. Another thing that they do, and here's something you need to highlight, is generalization. So again, if we're looking at a satellite image of this, the coniferous forest is not, that line is not going to be perfectly here, this mountain vegetation, the tundra line, that's not going to be exactly on the planet in real life as it is on the map. It's not, there's not going to be a real clear line, but in order to make the map easier to read, we've just got to kind of generalize it. That helps us get the information. So make sure that you have highlighted the word generalize in that statement too. Now, onto your next graphic organizer, we're going to record 3 methods of scale, okay? And they are fraction and ratio, a bar scale, or a written statement. So those are your 3 methods, and your examples are over here on the right-hand side. So there's what your fraction example is. There's your bar or graphic example, and then there's the written statement. 1 inch equals 1 mile. It could be 1 centimeter equals 100 miles, depending on the map. So these are your 3 methods, and these are the 3 examples that you'll want to write across from the method. Now let's talk a little bit about large scale and small scale. On the top of page 11, you have 2 boxes. And so you're going to have 2 yellow statements here to write. Maps are said to be large or small scale based on the ratio or that fraction compared to the Earth. So what math did we do to get from the globe to the actual map? So which fraction is larger? So this one on the left here, 10,000, 1/10,000 is the larger fraction. It's got the denominator that is lower, but that makes it the larger fraction. So the larger fraction means that it shows a smaller area of the Earth, but because it's showing a smaller area, it's showing more detail. So here's your second yellow statement. One way to remember difference between large scale and small scale. A large scale map shows individual features larger, meaning closer up and more detailed than small scale maps. So which map shows the largest scale? Correct answer is D, because it's in more detail, right? So we're showing a smaller area. That fraction is a bigger fraction, so we're showing more detail. Okay, here's the point where you're going to go to pages 18 and 19 or 20 and 21. The choice is yours. So turn to page 18. Oh, okay.